Okay, so for the next example, let's see what happens when now we're going to compare two different samples. So we certainly saw what happens in the case of permutation tests. So let's see how we can do bootstrapping when we've pulling data from two independent samples, such as in this case. So just to kind of get some background here, this data set is looking at the difference between the length of commercials on basic cable channels and on extended cable channels. So my understanding is extended cable channels would mean things that you don't get for free, so like HBO and Showtime and other things. And so the table below shows a number of minutes of randomly selected commercials that aired on both basic TV channel and extended TV channel. So we can see for the basic channel, we've got 10 values over here, and for the extended, we have 12 values. So this is not a matched pair example. We just took 10 random values corresponding to how long commercials were on basic TV in terms of minutes, and then so this is like in a 30-minute show, for example. One 30-minute show had 7 minutes of commercials, another had 10, and so on. And down here for the extended, one 30-minute show had 3.4 minutes of commercial time, and so on. So there's no natural pairing between these two values. They're two independent samples. So just to get a general sense, doing some exploratory data analysis, and if you're curious, this code, as well as the bootstrapping that we're about to do, is in a file that's up in Canvas called Cable Times.R. So first, I've defined these two variables, and we're going to use these shortly. So times basic is just the vector containing these 10 values up top. These are the 12 values that were in our extended sample. And then what we're looking at over here is actually the box plot. So you can make some histograms separately. If I want to compare the two side by side, a box plot might be a nice way to go. And then we can describe some summary statistics for each of those. So what we can see here is that it seems pretty clear that there are more commercials on basic channels than on the extended channels. So the median for the amount of commercials in a 30-minute show was about 9 for basic cable, and it's about a little less than 8 for extended cable. So there's some difference there. Is that difference big or not? Well, maybe bootstrapping will help give us a better sense of that. And so some other things that we're going to use in a second, so you might want to just recall, we're going to use these names for our sample for the basic times and our sample for the extended times. And I'm going to use this thing called nBasic and this thing called nxt to denote how many values were in the basic data set. So in other words, that would be 10. And how many values were in here? Well, that would be 12. But rather than use those numbers, I've assigned those values to these two variables. Okay, so how do we do bootstrap distribution for two different samples? So now I've got a sample of size m. So for example, we have our first sample that maybe is size 10, and we have another sample which is size 12. So they're not always going to be the same size. So what I do with my first sample of size m is I generate one bootstrap resample. Then I create a bootstrap resample from the second sample. So each of these should be the same size as their respective original samples. I calculate a statistic that compares these two groups. So for example, maybe I want to compare the mean amount of commercial time on basic to extended. So then after I've created a bootstrap sample from each of those samples, I would say, what's the mean of my basic bootstrap sample? What's the mean of my extended bootstrap sample? And then let me calculate what's the difference in those two means. And then I go back and repeat. And we do this over and over and over again. And then the bootstrap distribution, if we take this example out, we would then look at what are the distribution of all of the difference in means. So in this case, our statistic, we're trying to estimate, it doesn't help to write with the dot, the parameter that we're trying to estimate, theta, that's going to be the mean of the basic, say, minus the mean of the extended, and we're going to estimate that. So I'm going to put a hat on top of it with x bar, okay? And so each of these samples are going to be bootstrap samples, and so we're going to keep estimating this over and over and over again. And so one big disclaimer here is that we're not pulling these two samples together like we did with permutation tests. So there's no claim that there's no difference between these two populations. So in fact, we're going to keep them distinct. We're going to calculate their statistics separately, and we're going to compare those statistics and then look at the distribution of these differences. So let's just make sure we've got the general idea of what we're going to ask R to do for us. So here's the data set for the basic and extended commercial times. If I wanted to write out what is one possible bootstrap resample, well, I would get 1 from the basic times. So that might look like okay, maybe first I pick 10.2, then I pick 10.2, then 7.6, another 7.6, and another 7.6, and then I get a 7, and then I get an 11, I go back to 7, I get another 11, and we're going to do this, we're going to keep picking, put it back, and pick again until we've got 10 values. So I don't know how many I have here. Let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we would pick one more value. Let's make it a good one. Let's say it's 10.4. And that would be a possible bootstrap resample from the basic. And then we're going to do the same for the extended. So I pick a value. What's the first one I pick? Maybe I pick 7.8, and then 9.6, and then another 9.6, and then another 9.6, and oh my gosh, I got another 9.6, and then an 8.1, and we're going to just keep picking values until we have 12 of them. I've got a lot more to go. So let's say we get a 3.4, a 5.4, what did I say, 5.4, and then a 5, and an 8, and then an 8, and let's see, do I have enough? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then our very last value, again, let's make this a good one. Oop, I got 5. Okay, so these, I would pick a bootstrap sample from each of them separately, and then the next step would be, once I've got each of these bootstrap samples, I'm going to take the basic group, calculate the mean of that group. I take the extended group, I calculate the mean of that group, and then I calculate the difference of those two. I record that, I save that in some vector, and then I go back and generate a new bootstrap sample for each of them, calculate the means for each of them, calculate the difference, on and on and on and on. So that's what we're going to command R to do for us. Okay, so using the basic and extended cable samples, let's come up with a 90% bootstrap confidence interval to estimate the difference in the lengths of commercials, and then let's interpret what that means. So here's the code, and we're going to basically use the same sort of idea that we've been doing. So for this case, I chose to do 10,000 bootstrap samples, and I'm going to store all of my differences in this thing that I'm calling times.diff.mean. So right now, it's just an empty vector of 10,000 things. And now my for loop for each of these 10,000 things. Boot basic is going to be each of the Bootstrap samples I create from the basic sample. So I'm going to sample times basic. Those were the original 10 values that I had. I'm going to pick n basic. That was how many values there were. So this is equal to 10. And I'm going to pick with replacement. So this is just doing the Bootstrap sampling for the basic cable. This is going to do the Bootstrap sampling for the extended channels. And then before I create a new resamples, I'm going to take the mean of my basic Bootstrap. I'm going to take the mean of my extended Bootstrap and then calculate the difference in those two means. And that's, again, what's being stored in the times different mean. And now, once I've got all of that data, if I want to get a 90% confidence interval, that means I want the middle 90% of the values. So that means I'm going to look for the cutoffs that would be the 5th percentile and the 95th percentile. So we had to adjust these because previously we did a 95% Bootstrap confidence interval, and now we're doing a 90% Bootstrap confidence interval. And if you want to get a picture, you don't necessarily have to, but this is going to plot all of the values in our Bootstrap distribution, and this is going to put vertical lines at the observed difference that we saw, the lower cutoff for our confidence interval, and the upper cutoff for our confidence interval. And that we can see over here with some of the summary statistics of that Bootstrap distribution. And so just to explain where the 0.5 and the 0.95 come from, in between here, we want the middle 90%. So that means we're missing 10% would be outside of that middle, and 5% is over here, and 5% is over here. So that's where we came up with these cutoffs. So for example, that's the 5% over there, and over here, if 5% is above it, that means that would be the 95th percentile over there. And so what we can see, we get a 90% confidence interval, Bootstrap confidence interval. These cutoffs wind up being 1.193 and 3.435. So again, let me say this carefully. I'm going to attach the uncertainty to my interval. So I would say there's a 90% chance the interval from 1.193 to 3.435 minutes contains the actual difference in commercial time, mean commercial times, basic cable channels, and extended cable channels. And so what's of particular interest here is that all of the values in this interval are positive. So what that means is really the only plausible values that we're seeing are the fact that the basic cable times have longer commercials than the extended cable times.